The mathematical analysis of non-recursive algorithms. So far we have seen various examples of asymptotic complexity. Now the challenge is to give an algorithm and find its complexity. So how do we compute the actual asymptotic complexity of a given algorithm? So we will look at a few examples and we'll start with the easier examples. So we'll look at non-recursive algorithms. These are just algorithms which basically iterate through. So there are some loops, but there are no recursive function calls. So the specific algorithm, the example that we will start with, okay, is that we are given an array, unsorted array A of n integers, and what we want to do is we want to find the largest value in A, not necessarily the position. We can get the position also, but we just want to find the largest value. Okay, so what we do is we assume that A0 is the largest value, and then you scan the remaining. So you scan A1 to an minus 1, and you replace the current value by any larger value that we see. Right? So we start with an assumption that A0 is the largest, and then we go through from the beginning to end, and anytime we see a larger value than the one we have currently recorded as our maximum, we replace it. So let's first look at a formal statement of this algorithm. So here is pseudocode for this algorithm. So we have an algorithm called max element, which takes an array of size n with indices 0 to n minus 1. So as we said, we first initialize our maximum value to A0 and then we scan. Right? So this is the structure. It's fairly straightforward. So now to analyze this, we have to figure out how many steps this will take as a function of the input. So the first question we have to ask is, what is the input size? Okay. And in this case, it's fairly natural that it is n, the size of the array. Right? So it's going to take us less time for smaller arrays, a larger time for longer arrays. So n, the size of the array, is a natural input size. Now the next thing that we need to understand is, what are the basic operations? What is the structure of this program? Okay, so as we can see, there is an outer loop. So there is a for loop which happens n times, or n minus 1 times actually. And then inside the for loop, we have two things happening. We have, for every I, we have a condition check, ai greater than maxval. And if this condition is true, then we have an assignment of ai to the value maxval. So we have one or two basic operations per iteration. Now this one or two is a bit annoying, but as we have seen, in asymptotic complexity, we are not particularly concerned about factors of 1 or 2. So we can just take this as one basic operation per iteration and we'll be fine. So now let us write a function. So let us write C of n to denote the number of basic operations for input of size n. And now what we have seen is that we have to add up one basic operation for each iteration of the loop. How many loop iterations are there? Well, we go to the loop from I equal to 1 to n minus 1. So there are n minus 1 times we have to add up one basic operation. And if you think about this, this is just going to be n minus 1, because this is 1 plus 1 plus 1 n minus 1 times. And so therefore this algorithm is theta of n, because n minus 1 and n are related by theta, because in both directions you can find constant factors which keep them within each other. So this gives us a general strategy, or a general plan, as we can say. So the first thing that we have to do is we have to characterize the input size. You have to say, what is it that determines the input size? In this case, we declared that the size of the array is the input size. The second thing that we need to do is we need to identify the basic operations. So we have seen before that the basic operations are very simple usually. They're the ones which compare two values or which assign a value and so on. Then the third thing we have to identify is, how do these operations vary as the input varies. So in some cases, the number of operations is always the same for a given input. In other cases, the number of operations may be conditional. In our example, the conditional check if AI greater than max val. That occurs in every loop, so that will definitely happen n minus 1 times for every n. On the other hand, the assignment max val equal to AI happens only if the condition succeeds. So if we have these conditional things, then we have to be careful whether we are talking about worst case or best case, because if in the worst case, every time the condition would succeed and you would keep replacing. For example, if you had an array in ascending order, then in every iteration you would update max val. The best case is the very first element is the largest one, you never update max val. Or you might want to compute average case. So once we have basic operations whose behavior varies on different inputs, we have to worry about what kind of value we are actually calculating. But usually, I mean, unless we say otherwise, we can safely assume that we are always assuming worst case, because worst case is usually the one that is of interest and also the one that is relatively easy to estimate. Then after this, as we saw there, we set up some kind of a summation to add up across all the loops, iterations of the loop, how to count the basic operations. And the last step is to actually evaluate the sum. So in some examples like the one we just saw, you can actually add it up and get an explicit answer. Otherwise, you at least want to estimate the order of magnitude. Even if you can't get the exact answer, you want to know whether it's n or n squared or whatever. Okay? So this is our basic recipe now. We start by characterizing the input, we identify the basic operations, we check how these operations vary according to the input size, set up a sum to add them up and solve the summation. So since we'll be solving a lot of sums or summations, we should know some basic things, right? So we have to review some basics about summations. So there are first some simplifications or manipulations that one can do. So the first manipulation that one can do is move constants out. So if I have a summation of the form summation I equal to some lower bound to some upper bound of C times AI. So I have some values AL plus 1 and so on. Each is multiplied by a constant. Then this constant does not depend on the value of I. It doesn't depend on the position. So I can just take it out and I can simplify my summation to C times the summation I equal to L to U of AI. Okay, so this is the first simplification one could do. The second simplification that one could do very often is to rearrange and recombine. So we may have an outer summation over an expression. So I equal to L to U. So maybe we have AI plus BI. Now we may find it tedious to add up AI and BI, but recognize that we have A1 plus B1, A2 plus B2. So we can keep all the A's together, all the B's together, and this would be equivalent to I equal to L to U of AI, and then separately I equal to L to U of BI. Right? So you can add up the AI separately and the BI separately just by rearranging and reorganizing these sums, and you will get possibly two simpler sums. And needless to say, this would work also for minus. So supposing this had been AI minus BI, then you would have summation of AI minus the summation BI. Okay, so having simplified our formulas, let's look at some basic summations. So the first one is something we've already seen in a special case. So supposing we want to add up from some lower bound to upper bound, just the number 1. Okay, so we did it for, in our previous case, from 1 to n minus 1. Okay, so this is just going to be u minus l plus 1. So for instance, if you want to know how many numbers lie between 3 and 13, is 13 minus 3 plus 1, including 3 and 13. So you get actually not 10 but 11. So you have to be a bit careful about this plus 1. The other thing that happens very often in our analysis of algorithms is to add up from I equal to 1 to n, I itself. That is 1 plus 2 plus n. We want this sum. Okay, and this, as some of you may know, is n into n plus 1 by 2. So it's useful to kind of remember this, and an easy way to remember is to look at a nice proof by Gauss. Okay, so Gauss made the following observation. So he said, let's prove this. So let's write 1, 2, 3 up to say n. And then in the next row, let's write the same thing in reverse. So we write n, n minus 1, n minus 2 to 1. Okay. And now Gauss said let's add the sub-column y. So n plus 1 is n plus 1 of course. N minus 1 plus 2 is again n plus 1. So each of these columns adds up to n plus 1. How many columns are there? Well, there are n columns. So if I add up across all the columns, okay, then what I have is n columns times n plus 1. Right? So this is the total summation. Now, what does this sum represent? It represents the sum 1 to n once and the sum 1 to n again. So this is actually 2 times the summation I equal to 1 to n of I. Right? So therefore, since this is 2 times the summation, if I divide this by 2, okay, then I get exactly the summation I equal to 1 to n. So this is an easy way to remember this formula, that the summation I equal to 1 to n of I is just n into n plus 1 by 2. So let's move on to another example. So in this example, what we want to do is check if all elements in an array A are distinct. Right? So you have n elements, you want to check whether all n are different. So what you do is that you start with, for each I, you compare AI to everything to its right. AI plus 1, blah blah blah, up to an minus 1. Right? So if you find that AI is equal to something to its right, then you know that the elements are not all distinct. On the other hand, if you don't find AI equal to something, you go to AI plus 1 and do the same check. So in this way, if you go through this whole thing and you don't find any element which has any matching value to its right, then you know that all the elements are distinct. So once again, let's write down this as a formal algorithm. Right, so here's the algorithm, unique elements, which takes as input an array A from 0 to n minus 1. So what it does is it tries out each position in sequence. From 0, you only have to go to n minus 2, because once you reach n minus 1, there is nothing to its right. Remember, we want to compare each I to everything to its right, so we stop at n minus 2. So this is the first, this corresponds to this for each I. And now we want to check, go from I plus 1 to n minus 1. So basically for j equal to I plus 1 to n minus 1, and this is the second part of this thing. Okay. If you find AI is equal to AJ, then you know that your answer is false. And at the end of this, if you have never returned false, then you will return true. Okay. So once again, we want to analyze this. So the first thing we have to decide now is how many times this loop, this outer loop, is going to iterate. Because if you find AI equal to AJ, notice that this algorithm will exit prematurely. Right? So there are situations in which this algorithm will not go through the full set of iterations because you have this return inside the loop. So here is a case where we have to be careful about what we are estimating, and what we are really estimating is the worst case. Right? So what is the largest number of steps that this algorithm is going to take? So when is the worst case going to happen here? Well, there are two situations. The first is the easier one to understand, is that actually everything is distinct. So if everything is distinct, it means that this thing is always false. Right? So AI equal to AJ always fails, and so at every step you will always fail this check, so you'll go to the next one and you'll cycle through all possible values of I and J. The other thing which may happen is that at the last, right, the last step succeeds. So this is when an minus 1 or an minus 2 rather is actually equal to an minus 1. Right? So basically everything else fails, and then at the very last step, when you've gone through all the pairs, you find that an minus, so I is n minus 2 and j is n minus 1, and then you find ai is equal to aj, and then you return false. In either of these two situations, you hit the worst case. So this is the worst case that we are going to now estimate. How many times? So what is the basic operation here? The basic operation is this comparison. If ai equal to aj, so how many times is this comparison ai equal to aj executed in the worst case? So let's set up a summation for the outer loop as usual. So we say C of n is equal to, now in the outer loop I runs from 0 to n minus 2, and in the inner loop we saw that j runs from I plus 1 to n minus 1. and each of the inner loops we take one basic operation. So if we look at the inside, this is a summation of 1 from L to U. So we can simplify this using our earlier summation rule to say this is I equal to 0 to n minus 2 of the upper bound minus the lower bound plus 1. Right? So in n minus 1 minus I plus 1 plus 1, we can cancel a minus 1 and a plus 1, and we can further simplify this as I is equal to 0 to n minus 2 of n minus I minus 1. So this minus and plus gives us a minus I. So now how do we simplify this? Well, we could do some other things, but the simplest way is to just write out what happens for I equal to 0 to n minus. So when I is equal to 0, you have n minus 0 minus 1, so you have n minus 1. When I equal to 1, you'll have n minus 1 minus another 1, so you'll have n minus 2, and so on. And finally, the last step, when we have I is equal to n minus 2, we'll have n minus n will cancel, plus 2 minus 1, so we'll have plus 1. Right? So this is again something which we know. This is just equal to the summation from I is equal to 1 to n minus 1 of I. Right? This is 1 plus 2 up to n minus 1. And by our earlier summation, except we used n there, so we had n into n plus 1, so n is now n minus 1. So you have n minus 1 into n by 2. And some time back we had shown that this is just order n squared. In fact, it is theta n squared. Now let's look at a more traditional example from mathematics. Okay, so supposing we want to actually multiply two n cross n matrices. Okay, so call them A and B. Right, so we want to compute C, which is an n cross n matrix, as a product of A and B, and we know from basic linear algebra that each entry of the form Cij is going to be obtained by taking a row of A and a column of B. So you're going to get a sum of this form. You're going to have I0 and B0j, then you're going to have AI1 and B1j, and so on, and finally AIn minus 1 and Bn minus 1j. So this is how we compute the ijth entry, each entry in the final matrix C. Right? So this can be done using 3 nested loops. So let's look once again first at how this algorithm actually looks. Right? So this is our algorithm, matrix multiplication. It takes two n cross n matrices with indices 0 to n minus 1, 0 to n minus A and B, and it computes the output C. So it goes through all possible ij. So we want to compute Cij. So Cij for every possible ij is initialized to 0, and then we compute the sum that we just discussed, one element at a time. So for k equal to 0 to n minus 1, we add to the current Cij the new term Aik times Bkj. Right? So here it's quite easy to see that we have two basic operations. We have this basic operation happening inside 1, 2, 3 loops, and we have this basic operation happening inside 1, 2 loops. So let's first estimate the number of times this red operation happens. Well, that's very easy. So that's, we run I from 0 to n minus 1, and then we run j from 0 to n minus 1, and then we run k from 0 to n minus 1, and each of these is going to contribute a factor of n. So if we just simplify 3 times using our basic summation for, so this is the summation of 1, by the way. So if we use our basic thing 3 times, it's going to be n cubed. Okay, so this is intuitively clear and can also be formally justified by just applying this. If I do this, I will get n into n into n. Okay, so this is n cubed steps. And now this purple operation happens n squared times, and since n squared is a smaller order of magnitude, we can really discard it, and we can say that this overall algorithm takes n cubed steps. There is actually another way to see it in this particular case. So we have C has n squared entries, so we have to compute all of them, and each takes order n time to compute, because we have to run through n terms of the form Aik Bkj in order to compute a single Cij. right? So there are two different ways to estimate this complexity. One is to follow our recipe, which is to write out a summation and solve it. The other one is to make some observation about what you're computing and try to kind of count it in a different way. We have to update n squared values, and each of these n squared values takes linear time to compute. So for our final example, we will look at something where there is a loop, but the loop doesn't directly run n times. Okay? So the example here is to count the bits in the binary representation of a decimal number. Okay? For instance, if the input is 10, okay, then the binary representation of 10 is 1, 0, 1, 0, and so the answer is going to be 4. Okay, so we want to count the length of this, how many digits are there, how many binary digits, right? So the strategy here is that you keep dividing by 2 till you reach 1. Okay. So the way this would work for 10, for example, is that 10, so you will divide by 2 and get 5, and you will count, okay, this requires 1. Okay, now 5, you will kind of, when you divide this by 2, you're going to get 2.5, so you just keep 2, and you'll say this is 1 more. Now you divide this by 2, so you'll get 1, and then you say this requires 1 more, and then you'll divide this by 2, and you'll get 0, right? And you'll say this gets 1, and now you've reached the end, and so you have 4 digits. Okay, so this is the algorithm. So as we have done before, the first thing we will do is write out this algorithm formally. So here is a formal description of the algorithm, right? So we start by assuming that the number of digits is 1, and then we keep dividing by 2 at each step till we get down to numbers smaller than 1. And here, this operation here is the floor function, so this throws away the fractional part. So when you divide by 2, if you get a half, you throw it away. So now the point of this example is that this loop, although the input is n, this loop actually doesn't execute n times, right? So you start with n, and then you go to n by 2, and then you go to n by 4, and so on until n reaches 1, and this will happen after log 2 of n steps. So log 2 of n steps, you will end up with n is equal to 1, and that's because log 2 is precisely defined that way. How many times can you divide by 2 till you reach 1? Alternatively, starting with 1, how many times can you multiply by 2 to reach n? So that's the definition of log 2 of n, and so this loop actually takes log 2 of n. So the crucial thing here is that we don't have a summation which depends directly on n, but rather we have to look at the behavior of the loop and decide how many times it's going to, or compute how many times it's going to iterate. So another thing that we have to just to remind ourselves is that this is actually a sort of number theoretic function. So if we are really formally estimating its input, so the input size should be the number of digits in n. Okay, and the number of digits in n is actually, since it's a decimal number, is log 10 of n. But log 10 of n is a constant factor away from log 2 of n. It's just multiplied by or divided by log 2 of 10. And so this algorithm is actually linear, but that's not the point of this exercise. The point of this exercise is to show that the dependence of this loop on n could be not very obvious. It's not directly n or n squared or something, but something which really depends on something that's going on in the computation. So with these 4 examples, we have seen basically how we can start with an algorithm, okay, which in these simple examples was non-recursive, okay, and come up with some measure of its asymptotic complexity. And the idea is that we would like to set up a summation which expresses the number of basic operations, and then we solve the summation, right? So this is one simple class of algorithms for which you can follow this recipe and you can compute the complexity. What we will see in the next section of this chapter is how to do the same thing for recursive algorithms.